Hello, calculus students and general seekers of truth. Welcome to the lesson, section 2.6, on related rates. And this section is a lot of applications. There's not a whole lot of concepts here, or at least those concepts are best illustrated within the context of an example. So let's get right to it. A spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instant the radius is 30 centimeters? So we want to know the change. I mean, how fast is the radius increasing of the radius with respect to time? Okay, this is all with respect to time. So we can start out with a basic function here, the volume. Since this is spherical, the volume of a sphere is 4/3 pi r cubed. Okay. And normally this is all there is to it, but you can imagine, this picture is kind of like, here's a balloon, and it's getting bigger in every single direction. And not only is its size change, its radius is changing, of course, but the amount of gas that it's holding is also changing as well. Okay, so one of the actual major concepts in here is that these variables here, v and r, they are in fact variable, and they're changing with respect to time. So v is a function of time. Okay. R is also a function of time. Okay. So with this fact, we can take the derivative of both sides. So we can really think of this as this. This is really v of t is some function that describes the volume of the balloon is equal to 4/3 pi r of t is some other function that describes the radius of the balloon raised to the third power. So that's the main concept behind all of this. And now we can take the derivative with respect to v. So we can say that v prime of t, the derivative with respect to t, I said v, I really meant t, is equals to 4/3 pi. And here we're going to apply the chain rule, times 3 r of t squared times r prime of t. Okay, and I'm writing this out in function notation so you can see that v and r are functions with respect to t. But we actually don't need to write out as in function notation if we didn't really want to, because you'll see in a minute that it's really not that important in this particular example. It's really for conceptual understanding. So how fast is the radius of the balloon changing? So what we're looking for is, what is r prime of t equal to at the instant that the radius is 30 centimeters? Okay, so now we can basically just make some substitutions here. It's inflated, the balloon is being inflated at a rate of 800 cubic centimeters per minute. So that's v prime. That's the rate that the balloon is, the balloon's volume is changing. 4/3 pi times 3. R of t here is actually 30 at this moment. So 30 squared times r prime of t, and we're really solving for r prime of t. So now all that remains is to do some arithmetic. The 3's and the 3's cancel. You have, let's divide both sides by 4, and you have 200 equals 900 squared r prime of t, and there's a pi in there as well. So now, I don't know why I wrote 900 squared. It's just 900. Okay, that's 30 squared, and there's a pi here. So now we divide both sides by 900 and divide both sides by pi, and we get 2 over 9 pi is equal to r prime of t. In other words, at the very instant when the radius of this balloon is 30 centimeters, that's how fast the radius is changing. 2 over 9 pi. Let's get a decimal approximation of that. So that's about 0.071 centimeters per minute. Okay. So there you have it. A basic problem in related rates. The main ideas here are just to think about these variables and how they're changing and what they're changing with respect to. Most cases, they're changing with respect to time, but it's not always like that. Alrighty, so I'm going to end this video here. We'll start another one with a conical tank, and we'll walk through that example together. Thank you for watching. Have a wonderful day.